PhD student working in various ICCCE design research units of the department in UIA. And I'm co-author with Dr. Ibrahimy, Dr. S.M.A. Motakabber, and Dr. Zakir. And we have proposed a work that is called a compact bandpass filter using Microstrip Hairpin Resonator for WLAN applications. So let's look at the outlines of this presentation. The introduction part, we will talk about very basic things about our works and behind some reminders for you that we already have known. And then we will highlight some points. Now we have found some literature review, starting from 2013 to 2018, very recent trends. We'll talk about this. Then from there, we will show you the gaps and gaps of the designing bandpass filter. What are the major gaps still can be overcome? And then we set our goals in terms of the gaps. And after that, we will go straight forward to our theoretical consideration behind our design. And then we'll show the design and synthesis process. And after that, we'll talk about the results and the performance of the filter in terms of the results found. And then we will compare our works with the recent works that we already mentioned, the recent trends, the very recent works. After that, we will claim our contribution of the work. What are the major contributions of this research? And then we will make a conclusion at the end. So let's introduce with the filter first. We all know that filter is a kind of thing, especially for wireless communication. You may not notice it, but it's very obvious and very regular stuff, like your toothbrush, toothpaste, every day you use, but you don't feel it. So in the wireless communication system, filter is a kind of thing that you cannot avoid. To specify your channel, to specify a band, certain band, you need filters, bandpass filters. So for bandpass filter, there are some attributes, very common attributes you may already have known about this. The first thing is the bandwidth that we already mentioned. What's the bandwidth? It depends on the various things, but it determines how you are choosing a specific band. So the bandwidth is very important, the most important for a bandpass filter. Also, the insertion loss. It determines how much strength of signal you're losing in terms of insertion loss. If the insertion loss is high, then you will lose too many signal strength. So it's another important point of the bandpass. So another is like the reflection coefficient, that is one parameter. By the way, for designing higher frequency filter, we use the microstrip technique. Why? Because for because they are not suitable and they have self-resonance frequency in the high frequency band. That's why we don't use. We use the microstrip techniques because it's very with low profile, easy to fabricate, distributed elements. That's why we use microstrip. Let's look at the picture first to demonstrate what is the base of the microstrip. You see there are three layers. The top layer, we call it signal layer. We propagate signal through this layer. And we design, for example, for antenna we design patch. For filter we design resonator at the top plane, that was the signal plane. After that we have substrate as dielectric material with a specific dielectric permittivity. Sorry, I have this one. Okay, this is the dielectric permittivity, and this is the height of the substrate. This all determines something we will relate later on. And there is a ground plane. This is for grounding the signal. We can also work on here, for example, the defective ground structure. So by the way, for our case, for our design, we have chosen this 2.4 to 2.5 gigs as WLAN application and IC band application, the first band, according to IEEE 802.11 standard. And for this band, there are a lot of filters we have explored, and there are a lot of applications for this. Especially this band, as we even see, it's 2.4 to 2.5, so it's 100 megahertz. There are 9 channels according to this standard. So this 100 megahertz is very important to sharply select. If you select from the left side, our band signal, there may be some interference. So this is the kind of drawback that most recent works may have discussed in this section, the recent trends. This references you will find from my paper not here. It's very long, but we mostly focus on some good journals. ISA Web Science Index journals and also some good conference papers, starting from 2013 to 18. So what we have found is the recent trends. Recent trends means how the technique they have used for designing their filters. So the one technique is the interdigital lines. You all know that this kind of form line like that, interdigital lines. These are mostly for lowering the insertion loss to get a low insertion loss. Another is the fragmented loaded resonator. I found this in one paper only. I don't know why others didn't use, but it's a very interesting thing. Fragmented loaded resonators, and there's some spots over the top plane. It's like fragmented structure, and this is for compactness. This can make your filter very compact, very small size, very small size. Another is if you need further miniaturization, then you will use the defected ground structure that I already mentioned in the introduction part. You will defect the ground there, so that can make your filter more compact. And another is the self-coupled ring resonator. This is for also achieving low insertion loss. Another is the substrate integrated waveguide resonator. It's interesting that you use some holes for substrate integrated waveguide. It's also for compactness. This is hairpin resonator for high selectivity. That's interesting that only the hairpin resonator can sharply select your band. This is one of the good features of this. Also, step impedance resonator, coupled line, and radial styles for high selectivity insertion loss. So all this literature, they show either low insertion loss or miniaturization or high selectivity, but they cannot achieve these three things together, all together. Maybe one filter has a low insertion loss and compact, but in terms of selectivity of the bandwidth, it's been failed. Or it has a compact size and high selectivity, but insertion loss is high. So that's how we found the gaps. The gap is, in some filters, the insertion loss is high. That actually reduces your signal strength. After that, you see outband signal interference due to poor selectivity of WLAN bandwidth. We say the WLAN bandwidth is 100 megahertz. We select our, suppose, center frequency for 2.4 gigahertz. That will select some outband signals that will cause some interference in the WLAN frequency. Also, if the fractional bandwidth or the bandwidth of the filter is too high, then we need additional filtering elements to select that specific, WLAN 100 megahertz. So this is another drawback. That's the outband signal interference due to poor selectivity of WLAN bandwidth. Also, the filters are voluminous and cumbersome design. As I said, the fragmented structure or the defective ground structure, these are difficult to design and implement. And also, some filters are voluminous, that is unsuitable for integrated systems, or these days, some wearable systems we are using portable wearable systems to make mostly focus on antenna, but we additionally make use filters also. And you see, this is an interesting thing: inconsistent level of insertion loss within the WLAN bandwidth. If we consider the WLAN bandwidth of 100 megahertz, and if we see the level of insertion loss, then most of the filters they have no like something like maximally flat gain. So there's inconsistency of insertion loss. Mostly there's a peak at the top, the insertion is lost, and then suddenly rapidly goes down. So this is another drawback of the recent trends. So from there, we are proposing our goals. We are proposing a filter that can achieve the whole three things together, all the four things all together. The first is the low insertion loss. This is our primary target. Second thing is the high selectivity of WLAN bandwidth, as mentioned, 100 megahertz, which means we can sharply select this 100 megahertz band to reject the outband. Also, the filter has to be compact and with simple structure. And also, this one, the last one, the consistent level of low insertion loss within the WLAN bandwidth. So let's look at the theoretical considerations. Something like a mathematics and physics behind our work. So the first thing, we have chosen the second order ideal Chebyshev low pass filter prototype we have used to propose our design. And for that we have these element values like G1 to 3 like this. And then we need to transform. So we transform our filter into the bandpass filter with this frequency of 2.45. We have selected the center frequency as the center frequency of the W band. That's the important thing. Also the bandwidth of 100 megahertz. Then we use these classical equations. If someone is interested, they can explore. But the one thing I have to mention here, we have used the characteristic impedance technique to translate our theoretical design into microstrip level. So we use this equation where this W is very important. important, the width of the microstrip line that determines the characteristic impedance, and we all know that the length of the microstrip line that is related to the electrical length of the microstrip line. So then we go to the design part. It's something like hairpin that we are also lazy to use. Sorry, this is not for you. It's for wireless communication technique. So we have seen that there are two boards here. This structure, the hairpin structure, is mainly constituted with this. The basic thing is the loop. There's a rectangular loop. Also, there are two short-circuited comb lines coupled with the the larger stubs of this rectangular loop. So this is the basic filtering part, and this is the feed line. And we have used a kind of technique that is called stepped impedance. The width of this feed lines, then horizontally the width becomes narrow, and we have used a tapered line to match with this line. And for your information, there's a gap. You see this gap and this gap. These gaps are equal to each other. This G, and this determines the insertion loss of our structure. And the optimized value that we have found for this structure is 0.3 millimeters. And the width of all this hairpin structure, the basic one, is 0.4 millimeters. And we have used this 1 millimeter length and width for this short circuited stub. So this is the whole structure that we are using. Here, it is very interesting to see that this gap I said, it's the insertion loss, determines the insertion loss, is G. This L, the length, the comb line, and the rectangular larger stub. I mean L1, L2, L3, and L4. These are the scalable length. If you scale this, cut this, if you decrease the length of this L1, L2, L3, L4, then the frequency shifts to the higher frequency. And if you increase the length, just the opposite. Frequency going below 2.4 gigahertz, like that. Lower to the lower frequency. And this one, this L6 and L5, it determines the bandwidth. So for our design, we have considered this thing, three things. All these three things we are finding from this proposed design layout. And to just to represent our work in terms of equivalent circuit, lossless lump equivalent circuit, if we consider this, we all know for a microstrip structural line, if there is no grounding, then it together it's like a series inductor and capacitor. So in our case, we can see a lot of lines like that, but we have two lines that are connected to the ground. So this only two lines are like only inductor because this is an inductive valve. But for the other case, it's like this. And we all know that if there is an electric coupling between two comb lines, or between two lines, then there is a mutual capacitance. So that electric coupling is determined by this CM, like here and here. So this is our lossless equivalent circuit. And then let's look at the results of the performance of the filter. As we have targeted that our target was like from 2.4 to 2.5 is 100 megahertz. This is 3D magnetic, as you can see. It sharply selects the WLAN frequency. And if you look at the center frequency, it's 2.45 exactly. And the most interesting thing is, as we have targeted to achieve a maximally flat, because for Chebyshev response, we know that there's a ripple on the top. I mean, in this S11 and in S21, both ripple. But in our case, we have proposed something like a quasi-Chebyshev response. So for S11, we have second order response, like this, there's a ripple. But on the top, there's a maximally flat, which ensures a kind of consistent level of insertion loss, as we have mentioned here. So from here, you can see it's a consistent level of insertion loss that mostly covers this 100 megahertz bandwidth. So this is the S parameter response in WLAN region. And if you look at the wideband response, we see until 8.6 gigs, which means 3.5 of the center frequency times the center frequency, there is no spurious resonance. And let's look at this one. This is interesting. If I wish I could show you the video, but anyways, this is for the non-resonant mode. This structure actually works as a trap for electromagnetic signal because we have two short-circuited stubs and there is a step impedance resonator technique. So So when the signal comes to the port 1, you see this is with high current density. Actually, this area becomes too high with too high current density first. Then the signal comes, and then here also becomes high. So it's a kind of trapping like this, pumping the electromagnetic signal and releases on the second port. So it's a kind of technique that's very useful for oscillator application, because if you look at the group delay response, you will see that the group delay is a bit high at this resonant moment. So this is good for some specific applications like oscillator or something like that. So let's compare our works, the recent works. As you can see, only this work exactly has the center frequency of 2.45 gigs with a fractional bandwidth. If we talk about the WLAN frequency in terms of fractional bandwidth, it's supposed to be 4.08%. In our case, it's like 4.37%, which indicates that this design sharply selects the WLAN frequency. On the other case, only this has a kind of nearby result. By the way, so our insertion loss, our primary concern is 0.37 only, minus 0.37 dB, where the others, only one result or two results are something very close to this. Also, the level of S1 is good, and the area in terms of compactness, although it was not our primary concern, but still we have mentioned that it's compact. You see, yeah, it's okay to get claimed as compact filter. And we have used a substrate that is echoing Felix 8, very thin substrate that is good for portable or wearable or light applications. Others are like heavy substrate or thick substrate, FR4, R20 and like this. So the contributions that we can claim for our work, the lowest ever insertion loss in terms of this recent trends we have found at the center frequency of 4.5 GHz. High selectivity, as I said, the WLAN frequency is 100 MHz. We have selected 107.4, which is quite close to the exact frequency of this exact band of the WLAN that rejects the outband interference without further filtering element. Also, the filter is compact, as I said, thin, and it's good for integrating wearable systems. And the consistently low insertion loss that we have shown in the results section. The insertion loss level is better than, it's lower than minus 0.5 dB from 2.4 to 2.49 GHz, which means it's a 70 MHz within this band of 100 MHz. So this is the major thing that we can claim is interesting, because we have found from the position response. So these are the major contributions of this work. So finally, to conclude the thing is we have designed a Microstrip Hairpin Resonator based Bandpass filter to overcome the limitations of the recent works on the same point of interest. And we expect that our filter will be very suitable for WLAN and ICCCE applications. And the proposed design, we are still under work to implement and validate our work in terms of practical results as using these hierarchical structures. And our further target is to further miniaturize this filter to make it more compact. So that's all. Thank you very much for your question.